This is Unit 6, Inference for Categorical Data on Proportions. And in this video, we're going to learn about Topic 6.5, Interpreting P-Values. This is a direct continuation from 6.4. So remember, we're looking at a one-sample z-test for a population proportion. And we've already learned about steps 1 and 2. We're going to move into step 3 of the 4-step process. So let's just do a quick review. Step 1 is, of course, identifying the parameter of interest. A lot of kids say, do I have to do that? Do I need to do that? Yeah, you need to tell me what P is because, I mean, there's all kinds of P's out there. There's a proportion of kids that feel anxiety every day. There's a proportion of dogs that have rabies. The proportion of whales that are over 500 pounds. I mean, there's all kinds of proportions. So, every particular problem is dealing with a proportion. So you need to clearly identify what that proportion is for your problem. So yes, you got to do it. You got to name the test. It's a one-sample z-test for a population parameter. And in fact, you can actually do both of those things at one. Like I'll get a lot of kids that will say, this is a one-sample z-test for P, comma, the proportion of kids that have anxiety, right? So you can identify the parameter of interest in that name as well. But more importantly, or equally importantly, you have to write the null and the alternative hypotheses. And then step 2 is checking the conditions for a sampling distribution and then describing that sampling distribution by finding the mean, the standard deviation, and the shape of that. So all of this is super important as we move forward. So, here's the first example that we've been looking at, and let's just kind of run through it one more time. I want to make sure everybody's on the same page here. So a recent study found that a medical journal says that 35% of adults have experienced depression sometime in their lives. David, the mayor of a large town in Vermont, believes that residents of his town are much happier and are less depressed. He plans to sample 350 people from his town to hopefully prove it. So we were doing a one-sample z-test for P, the proportion of adults that have been depressed. So there you go. You can do all that at once. The null is that the P is 0.35. We're assuming that to be true. And the alternative is that it's less. That's what David believes. David believes his town, the true P, is less than 35%. All right, step 2 is building the sampling distribution. We're talking about the fact that, David's looking at one sample, but gosh, there's millions of samples out there. So the mean of all those samples is, 35% if we are going to assume that that is true. And the standard deviation is 0.0255. And then again, the shape is normal. Please make sure you check the conditions. I don't have them written here, but they should be, right? I'm going to assume that the sample is random to avoid bias. The sample of 350 adults from his town must be under 10% of all adults from his town to assume independence. And the shape is only going to be normal if there are enough successes and failures. And 35% of 350 is definitely bigger than 10. And 65% of 350, the not depressed, is also bigger or equal to 10. So I could use the normal shape. All right. So now we're moving on to step 3. Now we're ready for step 3, right? So we've done step 1, we've done step 2. Now, what's next? Well, what's next is we need some evidence, right? So in David's random sample of 350 people from his town, 91 said that they've experienced depression. That's a sample proportion of 26%, or 0.26. Is this enough evidence to prove that David is right and that his town is less depressed? That's our job moving forward. So in step 3, we're going to use this 26%, this P hat, as evidence. Now, let me kind of step back for 1 second. This whole concept of a one-sample z-test is really a lot like a criminal case, right? In law, where we have this true proportion that is sitting here telling us, I'm correct. I did it. I'm correct. I'm not wrong. So that's what's happening here, right? We have, we read that 35% of people experience depression, and that P, that proportion, is screaming, I'm correct, I'm correct, I'm correct. But again, it's just like a criminal law case, right? We got to go through the procedure. So the first thing that we got to do is, because David is accusing this proportion of being wrong. He believes it's less. So, first off, if this was a criminal court case, if somebody was being accused of murder, well, the first thing that happens is they go in for their arraignment, right? And they get a name, right? They get a number. Their trial, their whole court case gets a number, right? And that's the name. That's step 1. It gets a name. And then the judge is going to say, how do you plead? And the guy says, I'm not guilty. I didn't do it. And that's what's happening, right? And then the prosecutor is on the other side with the alternative saying, no, we think you did do it. So that's exactly step one, right? Step one is this whole thing gets a name, a one sample Z test for the proportion of people who have depression in this town. And then the null and the alternative is, again, that plea hearing where the null is saying, no, I'm true, I'm correct, I'm true, 35% is true. And then the alternative is the prosecution is sitting there saying, no, sorry, I think it's lower, I think the truth is lower. And then, in any criminal court case, there's all kinds of legality, all kinds of, official things that have to happen. That's kind of what step two is about, right? And if you know anything about criminal law, maybe watch a couple episodes of Law and Order, you know that you have to assume innocence. The jury's job that's going to make the final decision is they have to assume that guy who says, I didn't do it, I'm not guilty, we got to assume that he's telling the truth. So that's exactly what step two is, right? Step two is us saying, okay, well, P, you're telling me you're correct. You're telling me that the truth is 35%. So I'm going to build a sampling distribution showing me what all possible samples will look like on the assumption that you're telling me the truth. Now comes the prosecutor's turn to find that evidence. And the evidence that prosecutor is going to use in a statistical example is a sample proportion. All right, so now we're ready for step three. So in step three, our sample proportion comes into play. It's time to put our thought to the test. Okay, now everything's set up. We're all good to go. Basically what happens is that we have two things to do in step three. The first thing we have to do is find the z-score of our sample proportion. We have to determine, is our sample proportion, how far is it from the mean? Is it really high, really low, or, kind of in the middle? That's the z-score's job. And then we have to find the p-value. I'll explain what a p-value is in a lot more detail here shortly. But let's start with the z-score. Now, a z-score is called a test statistic. Now, I haven't really used that term a lot. We've been saying z-score, but a z-score is a test statistic. It is how many standard deviations from the mean our sample proportion falls. So it's a synonym, right? So it's just two different words that essentially mean the same thing. So a z-score and a test statistic are essentially the same thing, right? So generically, a test statistic is taking a statistic, right? In our case, a p-hat, and subtracting what we believe to be true. That's the null parameter, what we believe to be true, and dividing it by the standard deviation of the sample proportion or the sampling distribution, right? So in a little bit more, symbols here, here's what a z-score or a test statistic is. It's our sample proportion p-hat, the sample we're using for evidence, minus the null proportion. That's why I put this little zero right here. That's just representing the null, right? It's the proportion that we thought was true from the null. And we're going to divide that by the standard deviation. And this next form is really just the same thing here. All I did was replace the standard deviation with the formula. Remember, the formula for standard deviation is taking that assumed truth, p times 1 minus p divided by n, all inside the square root. So that's just showing the standard deviation as its formula, okay? So remember what the z-score is going to do is it's going to kind of tell us how far from the mean our sample proportion is. And this is why I love drawing a picture, because when you have a picture of your sampling distribution, you could say, okay, you're telling me the truth is right here in the middle. You're telling me that that's the truth. Now I'm going to find a sample, because remember, this sampling distribution represents millions of samples. And what I want to do with my sample, what I want to do with my p-hat is I want to determine where's it at. Is it just a little bit bigger, or just a little bit smaller, or is it really small, or really big? And that would be some good, strong evidence. All right. Now the p-value, and let me take a quick time out here to explain something. There's lots of p's going on in this problem, right? The whole thing is beginning with p, right? Look at your null and your alternative hypotheses. They use the letter p for the proportion. But this is a very different p, and that's why we actually label it a p-value. When we talk about a p-value, we are not talking about a proportion of people who feel depressed, or a proportion of kids who feel anxiety, or a proportion of whales that have some type of virus, right? No. We add the hyphen value to emphasize a p-value is a probability. It's not a proportion. So we don't, there's, again, lots of p's going on here. So that's why we don't want to use just plain old p, because you might confuse it with the proportion from the problem, a p-value is a probability. So by definition, the p-value is the probability of a sample proportion occurring as extreme or more extreme than the observed sample proportion on the assumption that the null hypothesis is true. Remember, everything has to be on the assumption that the null is true. We're believing that the p that we have as our null is telling the truth, right? So, what this looks like, a little bit more mathematically is we're finding the probability. So there's the p for probability. We're finding the probability that a sample proportion, p hat, don't forget the little hat, a sample proportion is greater than or equal to our observed p hat, the one that we found in our sample. Now, we could also look less than, right? I actually have this symbol wrong here. We could look less than. Okay, we could look either way. Please remember, extreme means two things. If it's cold outside, extremely would mean even colder. If it's hot outside, extremely hot would mean even hotter, right? So it could be either direction. So if we have a p hat that's pretty high, then extreme would mean even higher, even greater. And if we have a p hat that's pretty low, then or more extreme would be even lower, okay? So now remember, this is equivalent to us finding the probability of a z-score being greater than our test statistic. Because remember, our test statistic was calculated based on that p hat. So we have to write it two ways. We have to write it kind of, using the p hat, the proportion from our sample, and then we also have to write it using our z-score, because that's how we're actually going to calculate this, right? To actually go and get this probability, we need to go and use normal CDF on our calculator. Normal CDF will get you probabilities with a normal model, which of course we're working with here. So that's why we have to make sure that we're using z-scores, because that's the only language that normal CDF speaks in. All right, so let's talk a little bit more about the p-value real quick here. If you want to kind of explain this a little bit easier, right? The p-value is simply telling us how likely our sample proportion or more extreme is on the assumption that the null hypothesis is true. So if we think back to the problem that we're using in this video for David and his depression in his town, the p-value would be the probability of a sample proportion coming back lower or equal to the sample proportion that he got of 26%. Okay, so his sample was 26%. So we need to find the probability that a sample comes back equal or lower than that. That's the probability. Why am I looking lower? Well, go back to the null. The null was 35%, right? We believed it was lower. So that's why we're looking lower. Now, let's make a couple notes about this. Just want to make sure this is very clear. If your alternative hypothesis is that we believe the population proportion to be less than what we thought it was, then we were going to be using the word more extreme to mean lower. If the alternative hypothesis is that we believe the population proportion to be greater than what we said it was in the null, then the phrase more extreme would mean higher. So, a lot of kids say, where do I look? Do I look above or do I look below? It all depends on where your alternative is. Does that make sense? Now, here's the only tricky thing. The only thing you got to be really careful of is if our alternative hypothesis is that we believe the population proportion to be different, meaning we don't really care if it's higher or lower, we just mean different, right? In this case, more extreme could be lower or higher, all depends. Well, if you think about it, we can only ever explore one side at a time, right? When it comes down to looking at evidence, we either have evidence that's lower or we have evidence that's higher. But the difference is if your alternative is not equal to, then all you have to do is once you find that p-value, you have to double it. You just have to multiply it by 2. And that's why we call it a two-sided test. So remember, if all we care about is that we believe it to be higher or we believe the truth to be lower, that's called a one-sided test. If we just care that it's something other than what we were told, that's a two-sided test, so you have to double your p-value. We're going to look at an example like that towards the end of this video, so I think that'll be a little bit clearer. All right, let's go back to our example so we can see how all this plays out. All right, back to the example. 35% of people experience depression in their lives. David thinks it's lower for his town. He goes and gets a sample, 350 random people. 91 said yes, they feel depressed. That's 26%. All right, now what we're going to do is find the z-score, also known as the test statistic, and the p-value for our proportion. It's actually so easy. Now, remember, when you're doing this, you have step 2 right above step 3. So everything should be kind of lining up. So first, we're going to find the z-score. Where does 26% fall? To do this, we're going to subtract the thought to be truth, 35%, and we're going to divide by the standard deviation, and that gives us negative 3.5294. If we quickly go back to step 2, which again, on an actual problem, this would be right above step 3, we could literally locate this, right? We could see that where does 26% fall? Oh my gosh, it falls way down here somewhere, right? Not -1, not -2, not even -3. It's negative 3.5, right? It's somewhere down. It's way down there. So that is what the z-score tells us. It's telling us exactly where our data falls, where our sample falls on the model that we built. Okay, then we got to find our p-value. So remember, since our alternative was that we believe, or David believes, that it's less than, we're going to look below. So the probability that a sample is less than or equal to our sample would be equivalent to the probability of a z-score being less than or equal to negative 3.5294. And I'm going to find that probability using normal CDF. Again, I've been emphasizing this for units now. You got to show your work here. You got to write this down on the paper, normal CDF. And when we do truly look below, remember we look below by starting at negative infinity. Now remember, on our calculators, we don't have an infinity button, so we usually use negative 99. And then we go to our z-score of negative 3.5294. We find that this to be a very, very, very unlikely probability. Once again, we could go back to our picture to actually see this probability. The probability that a sample comes back 26% or lower would be a very teeny tiny amount. Remember, 26% is already low. To look even lower would be minuscule, right? Very, very small. And that is, again, exactly why our p-value is what it is, a very low number. All right, so now the only thing we have to do is we got to make sure we explain the p-value, right? I cannot tell you how important it is for you to understand what a p-value is. It's really one of the biggest topics in all of AP statistics because p-values are so commonly used. So let's make sure we once again, in purple here, know the definition, right? The basic generic definition of a p-value is it's the probability of the sample proportion occurring as extreme or more extreme than the observed sample proportion we saw, okay, on the assumption that the null hypothesis is true. Let me kind of take a quick pause right here. Again, compare this to a criminal court case. We have this criminal who we have accused of murder. We have him on the trial, and he's saying, I'm innocent, I'm innocent, I'm not guilty, I'm not guilty, I'm not guilty, I didn't do it. And what I'm going to do is I'm going to say, well, okay, I will assume that you are telling the truth. But I have evidence that shows your fingerprints are on the murder weapon. I have 2 eyewitnesses who saw you commit the murder. I have somebody else who tells me that you had motive. You owed this guy $10,000 and you didn't have the money to pay it. So I got motive, right? And then you know what else? I got DNA evidence. I got your blood on the victim's clothes. I got the victim's blood on your clothes. Listen, pal. What do you think the probability of all that evidence being true is and you still be innocent? And he's going to look at me and say, yeah, I get it. Not very likely. And that's exactly what the jury's thinking. Wait a minute. All that information you just told me is true and you want me to think he's innocent? Gosh, that is very unlikely. And that is why we're going to put the guy away to jail and claim he's guilty. So that's exactly what a p-value is, right? It's looking for the probability of this evidence or more extreme on the assumption that the null is true. So what is our p-value in context? It is the probability of getting a sample proportion of 26% or lower from a random sample of 350 adults is 0.0208%, right? So it's very, very unlikely. So the probability of getting such a low sample or even lower is 0.0208%. And again, this is assuming that the population proportion is 35%. So we were believing the null. We were believing that the truth is 35%. And what we just found out is that it's very, very unlikely. But it happened, okay? Now, that's it for step 3. Step 3, all you got to do is provide for me a z-score, showing just a little bit of work, and provide for me a p-value, showing me a little bit of work. Now, the final step, which will be in the next topic video for 6.6, I'll give you a little preview here. The final step is making a conclusion. Now, I don't want to spoil anything here because there's a whole nother video coming for that next step. But we need to make a conclusion, right? That's the next step. We need to make a conclusion. Does Mayor David have evidence that his town is less depressed? Well, just think about that for a second. Since our sample of 26% was so unlikely, assuming that 25% was true, then the only conclusion could be made is that, yes, Mayor David does have evidence that his town is less depressed than the rest of the country, right? Plenty more details to come in terms of the conclusion, but essentially that's it, right? Something unbelievably unlikely did happen. The only conclusion could be that David's right. We'll talk a lot more about that conclusion in the next video. All right, let's end this with one more example. I would suggest just kind of watching if you want to work with me, but just kind of watching and hearing it all kind of unfold should make a lot of sense. All right, news report claims that 62% of all students experience daily anxiety. Cool. Sally wonders if the truth in her school district is something different than that. She just wonders if it's different. So she goes and gets a sample of 220 students, random sample from her school district, and 66% of them felt daily anxiety. Does she have evidence that her school district is different than the rest of the country? Let's go ahead and do steps 1 through 3, and we'll even give you a little preview of step 4. All right, step 1. This is a one sample z-test for P, the proportion of students that feel daily anxiety at Sally's school. My null is that, well, I'm going to go ahead and assume that the truth is 62%. I'm going to go ahead and say that this P is telling the truth and that the real proportion at Sally's school is 62%. But the alternative is that maybe Sally's on to something here, and that Sally believes that her school's different. Now remember, different doesn't mean higher or lower. It means either. It's just something different. So that's why I'm using a not equal to sign. So this is a two-tailed test, a two-sided test. All right, step 2 is going ahead and building a sampling distribution, assuming that 62% is true. So a sampling distribution shows a whole bunch of sample proportions. So the mean of all those sample proportions is 0.62, assuming it's true. The standard deviation utilizes 0.62 times 0.38 divided by our sample size of 220, giant square root, 0.0327, and then I could draw a picture. Now, I did write out the conditions very nicely. The sample was random to avoid bias. The sample size of 220 is assumed to be less than 10% of all students in her school district, so we could assume independence. And the sample had 146 students that did report daily anxiety and 75 that did not, so the sampling distribution will be normal. Both of those numbers are bigger than 10. All right, so this is a nice picture of the sampling distribution. So this is, again, I'm allowing the accused murderer to be true. I'm allowing him to say he didn't do it. Now it's time for us to look at our sample. Our sample, Sally's sample revealed that 66% of kids from her school felt depressed, from her school district. So the z-score for that proportion is 0.66 minus the assumed truth divided by the standard deviation, and her z-score was 1.2232. So if you look at the picture here, 0.66 falls just a little bit above the mean. Really doesn't seem to be that high at all. Now, the p-value is the probability of her sample occurring, or more extreme. Now, since her sample is positive, it's higher than what we thought was true. 66 is bigger than 62. We're going to look even higher. So we're finding the probability that a sample is greater than Sally's sample of 0.66, which is equivalent to a z-score being greater than 1.2232. Going to use normal CDF to find that by looking at 1.2232 to infinity, and I get 0.1106. Now, I'm going to double that. I'm going to multiply that by 2. Why? Because the alternative was not equal to 0.62, right? Meaning that she didn't really care if the sample proportion was higher or lower. She doesn't really care. She just cares. She's just wondering, is her school different? So, yes, her one sample came back on the high side, But if it would have came back on the low side, she would be wondering the same thing. Is her school different? So that's why we double it. Now remember, because of symmetry, both sides of a normal model are the same. Now, let me briefly talk about why we did not do that with David's example. Think about this for a second. David was only wondering if his town was less depressed. Let's just play a game real quick. Let's just say that David's sample came back at 40%. I think David would probably just shut his mouth, close his door, and pretend none of this happened. Because if a sample came back higher than what we read was true, then David is completely wrong. There is no need to even move further with David's test because David thought it was less than 35%. So if David's sample came back higher, then we'd be like, David, what are you doing? You're clearly wrong. Stop, you're wrong. It's not less than 35%. Your dang sample came back more. But in this problem, Sally, she didn't really care if it was more or less. That's why we have to double it because it could have been on either side. All right, so now we just have to make sure we explain her p-value. Her p-value is the probability of getting a sample proportion of 66% or more extreme. I didn't say higher, I didn't say lower, just said or more extreme. Could be in either direction because it's a two-sided test. And that probability, that p-value was 22.12% on the assumption that the proportion is 62%. Now, this is very likely. What this means is that her sample was not weird. It was not significant. It wasn't that odd at all. So what conclusion would we make here? I'll give you a little preview. It's basically saying that, listen, Sally, your school is not different than 62%, right? Yeah, your sample came back a little higher, but it was only a little higher. It wasn't that weird. So we do not have evidence that her school is different than the nation value of 62%. Even though her sample didn't come back 62%, it came back 66%. It was just a little higher. It wasn't unbelievably higher. So that is why our conclusion would be, sorry, Sally, you are wrong. Your school is not different, all right? But we're going to talk a lot more about the conclusion in the next topic. So stay tuned. That's it. Basically, step 3 is finding the z-score, which we also call test statistic, and the p-value.